Okay, so we are the B project. Joel, Firuz, and Isabel are undergraduates, and Maggie, myself, and Alan are high schoolers, and our mentor was Professor Richard Martin.
So first for our project, we're going to talk about motivation a little bit. So just as a fact, every year, approximately 10% of bees die to natural causes. And however, recently research shows that upwards of 30% or more have been dying. So we wanted to make a system that is able to count the amount of bees entering and exiting a beehive in order to be able to address a possible decline in population. So as you see on the screen, this is our general schematic of our system we want to build. So the solar panel on the left is going to power a Raspberry Pi single board computer. And then attached to that computer is a camera. And this camera will be filming the entrance point that the bees travel into the hive. And using computer vision software, would be able to count the amount of bees, send that count via radio all the way back to the laboratory here. And we're going to talk more about each step in detail.
So now we're going to talk about how we're going to actually count the bees. So initially we were thinking about using a model called YOLO V4, and that's a CNN, convolutional neural network deep learning technique. But the problem with this technique is that we're running our code on a Raspberry Pi, and a Raspberry Pi does not have that much processing power. So we have to sacrifice processing power for accuracy. And we decided to go on with the background subtraction technique instead. So basically, how background subtraction works is that it detects any objects that are moving on your camera screen. And in this instance, we're detecting bees which are moving. So the algorithm which we're using is called k-nearest neighbors algorithms. And then you can see on our graph over here, our accuracy rate increases as our frame count increases. So overall, our accuracy rate is 60.4%. But if you just take into account the last 500 frames, our accuracy rate is 92.64. In order to limit the noise, we included Gaussian blur to our algorithm, but there was still some errors. The main problem with this algorithm is that if you can look at this picture over here, this bee was not detected. That is a little bit bigger than the other types of bees because it's a drone bee rather than a worker bee. Another problem was that this algorithm only detects bees that are moving rather than stagnant bees. So in order to make our algorithm more accurate, we decided to go with color here.
So this technique we tried to design it to fix some of the problems we were having with background subtraction. So for example, the stagnant bees, we'd be able to count those. So this algorithm works in a similar fashion that it picks certain pixels to circle and counts that towards the count of bees. However, it counts them in a different way. So with background subtraction, it counted them whether they were moving or not. In this situation, it counts them based on a specific range of color that we import into the program. So just on the right, you can see that there's two types of color representation. We used HSV because it's more accurate for a computer to read. And so you can see it's hue. So that's like the quality of the color, like red, orange, yellow, etc. And then the saturation and the value tell you the brightness and the dimness of the color. So what we did was just use a specific range of yellow with all of the saturation, all of the values to find the colors of the bees. So in this, you can see on the left, this was the output of the algorithm, and it circles each bee, and it has the correct count on the top left of 13. And it bases that count off of its color. And you can see on the next slide, on the left is our actual setup. So you can see like the radio, the camera. We're going to talk more about the radio and the weatherproof case in a second. But you also have, we didn't film this on the Beehive, so my computer is just running a video of bees, and then the power source in the back. And you can see on the right, again, similar as to before, it circles all the detected bees and counts them in the terminal. So one issue with this process is that if the background is not yellow, then, if the background is yellow or a similar color to the bees, then it would mess with the count. So that's something, you have to make sure that the background is not the same color.
So to send our data, we chose to use a LoRa, which is a long-range radio, because it can send small amounts of data over a long distance using a low amount of power. So the theoretical claim by LoRa was that it could, the two modules could transfer data over a distance of around 2 miles within line of sight So considering that the Fort Farm where the Beehive is located is about a mile away from the lab, we thought that that would be sufficient to prove the success of the project. And so the LoRa radios use a I2C, which is a integrated circuit serial communication protocol. Basically, they send and receive data in packets. So we created a code in Circuit Python that configures the radio and uses the OpenCV to calculate the bees and then send just the number of bees and also the number of the packet to the other radio. For our power supply, we were using a solar panel that could generate 100 watts of power on a sunny day, but more realistically, if it's more cloudy, it would be around a couple, like 5 watts, maybe a couple. Considering that our Raspberry Pi needs 5 volts, it was realistic that it would be sufficient for us. And here in the picture, you can see the power supply, which is connected to the charge controller. And then we soldered a 12 voltage socket to it so that we could use a USB-C to micro USB cable to plug it directly into the Pi. And after testing, we received a sufficient amount of current, which is about half an amp.
So originally, we had planned to use the audio from the Raspberry Pi to also increase the accuracy of our computer vision algorithm. However, because we quickly found out that the amplitude, or how loud the sound is, wasn't a very good indicator of how many bees there were. Because if a bee flew close to the microphone, then the amplitude or the loudness would increase by a lot, and that would just mess up the entire algorithm. So instead, we decided to use the other part of the sound signal, which is the frequency, or the pitch. So we can see that different bees make different pitch buzzing when they're doing different things. So although it's not as clear in this image, the bees performing orientation flights, which are when new bees from a hive are introduced to the outside world, the pitch is slightly higher, as you can see by the more red higher up. We'd also like to be able to detect if there are angry hives, although we don't have audio of that yet. And to process this audio better, we've removed most of background noise by running a high frequency filter or a low pass filter, which removes all of the audio above a certain frequency level. As you see here, all this blue means that there's very little noise there. And these graphs show red is high amplitude or high noise, and blue is low amplitude or low noise. So we see that buzzing of the bees is primarily in these low frequency or low pitch regions.
So as for our results, we were able to get the algorithm so that it was 90% accurate, and we were able to do this using half an amp of current to power the whole system. And since this system is going to be outside near a beehive, we need to weatherproof it. So in the top image, you can see our weatherproof case that has the radio sticking out and cords that need to stick out are sticking out the back, and then the whole system is on the bottom picture. And we got the 2 radios to send data from about half a mile away from each other.
So in the future, since we couldn't send the data for over 2 miles from the farm to WINLAB, we were only able to send half a mile. So what we can do is that we can install a different radio in between as a relay node in order to make this transition more feasible. Another part of the project we can work on in the future is that it's basically uploading the data that we have that is collected on the Raspberry Pi to the cloud server so that we can perform more accurate and manual automatic processing and calculations. In addition to that, in order to increase the accuracy of the bees detection and in order to see how well the beehive is working, we can also install temperature and humidity sensors on the beehive itself. And finally, we can test the accuracy of our entire beehive over long periods of distances. But dear audience, bees are extremely vital to our ecosystem. They're huge pollinators for our crops. And on top of that, they're extremely vital to our food supply. So let's save the bees. Thank you.
So, does anyone have any questions?
My question is, nice work. So my question is like, why you do the audio another?
So the initial plan was to use the pitch, the amplitude or how loud the beats were to improve the computer vision algorithm, because at the time the computer vision algorithm wasn't perfect. But then we quickly realized that that wouldn't really work out. But we had the audio, and we thought that we could use it to see other states of the bees. So orientation flights are a sign of more new hive activity. So a healthy hive will have plenty of orientation flights. So by being able to detect those orientation flights that happen at a different pitch, we can still tell if the hive is healthy or not.
So how do you define angry hive? I don't understand.
So when a hive is agitated, the bees will come out and be more active around the hive. If there's like a predator or something attacking the hive, that's what I mean by angry.
And how do you define the accuracy? Like, so compare what to what, like your prediction with actual count. But how do you count the actual?
So basically what we're doing is that our theoretical overall goal is to gather data from the multiple different sensors, audio, computer vision, as well as temperature and humidity. And we use a combination of these different sensors in order to determine the state of the beehive. Just going off of computer vision alone or audio alone is not going to make our algorithm accurate per se. So
No, I mean, it not doesn't say it's accurate. You have to like you know the real population of the bees, right? But how do you define the real population of the bees?
So our judge for accuracy was, we compared the number of bees counted by our computer vision algorithm to the actual number of bees in the frame.
The thing about this decline in the bees is that it's not actually known how many bees are needed for the hive to definitely survive. So instead of like knowing the whole population of the bees, we're just focusing on the entrance because we can know a lot about from the entrance. Seeing it just alone, if a lot of bees are exiting or entering, can show if the hive is healthy. So we're never actually going to know the entire population of the beehive because that's still research is being done on that, and it's very like kind of unknown how many bees are needed. It's more about the rapid decline rather than the number of the bees themselves.
I just want to have a basic idea, like how many bees in a beehive. I don't have any idea. So
I mean, on average, with here I can go back a few slides. Let's see here. Like here, for example, I mean, you can see that's just the entrance point. So it's like 20. You know, it ranges, but I mean, the whole point is just to see like the rate, not necessarily the count. So even if it's off by 10%, if it's decreasing or increasing, it'll still be relative. So.
thank you so much.
So you based it on the image, right? Not the actual image.
Yeah, I mean, optimally we would have like implemented the whole system, but you know the radios didn't connect. We made a few visits and like tried to find the best camera orientation. But, yeah, it would require more work. So, yeah.
So you based not just picture, right? You are on the video, right? You are based on the video for the research.
Sorry.
Is this based on the video on the?
Yeah. It's just a snippet.
So a beehive has 6,000 to 12,000 bees in it, but we're only looking at those that are entering and exiting because that's still a good sign of how many bees are left in the hive. Because a certain percentage of them will be entering and exiting the hive constantly.
Okay, so let's leave some questions for poster
Okay.
session.
All right, thank you, Gavin.